Hello everyone, my name is Carmen and today I will present my critical paper. The precise control of a robot depends on these mathematical models. The reference paper by Fans and Collins proposed a robust theoretical solution using dual quaternions, but its main limitation was the lack of direct experimental comparison against other methods. My work fills this gap and asking, does the theoretical adaptation translate into superior practical performance? This is the central critical of my project. We work in MATLAB with the robotics toolbox to model the manipulator. On top of that, I programmed many core functions, two for forward cinematic, two for Jacobians, the axis angle conventions, and this iterative control locked up integrate everything. The control we use is the Jacobian self-inverse, which minimizes the post-error in each iteration. The self-inverse J plus in computer with the MATLAB function P. The gain cap was set as an identity matrix scaled by a factor. K equals 1 for axis angle and K equals 0.5 for dual quaternions. In the axis angle case, the pose is a six-dimensional vector, three values of the quaternion positions and three values for the orientation and rotation vector. These seed values come from the homogeneous transformation matrix. The last column gives the positions, and the rotation part is converted into axis angle form. The problem is that subtracting two rotation vectors is only approximation in CO3, valid only for small angles. This figure shows the two algorithms follows: axis angle on the left and dual quaternion of the right. The sleep are the same: initialization, loops, forward cinematic, errors calculation, update, and stop. The difference essential is in the error. Axis angle use a approximation, while the dual quaternion use a valid vector operation. We define two scenarios. Scenario one is a long-range motion, and scenario two is a short-range motion. Both start from the same initial configuration and definite Hastenberg configuration. In scenario one, the motion is large. Look at the blue curve for dual quaternion. It's just 5 iterations, the error rate drops below 1 and converge in 16 iterations. Now look at the orange curve for axis angle. Instead of decreasing and oscillating violet, it never stabilizes and never converges. This catastrophic instability is the experimental proof of the theoretical weakness of axis angle. The errors extraction is 03 is not valid. In scenario 2, the motion is small. I'm ball controller converts, but look at the different interfaces. Dual quaternion starting a small inter-error of 0.5 and converts smallly in 10 iterations. Axis angle start much grow with internal errors of 2.6. In decreasing slowly and need 14 iterations, more than 4 times the effort of dual quaternion. This graph gives the proof of the reference paper was missing. For bigger motions, axis angle fails. For small motion, this works, but slow and give. Dual quaternion works in all cases, fast and stable. This difference shows that dual quaternions are not only theory, but also range solutions for robot control. In conclusion, a six angle is straight and reliable. Dual quaternion are robots fast and reliable. This critical paper demonstrates the missing experimental validation for future works. We recommend testing the Jacobian transpose controller, validating on that physical robot, and extending the trajectory tracking task. Thank you.